Oh, sorry, am I the first speaker?
No, you're the last speaker. How do you pronounce
it? Just to test if I can share my screen, right?
Well, no, yeah, we just wanted to test real quickly if it works.
Okay, okay.
We'll start the session.
So where is the share screen button?
It should be in the bottom. So if you sort of hover over the bottom, there's participants chat share screen.
I saw it.
Yeah. Okay, good.
Yeah, can you see my screen?
Yeah, I can. Yeah.
Okay, thanks.
Okay. So again, 1 second. How do I pronounce your name?
Jianan.
Jianan?
Yeah.
Okay.
Yeah.
I'll try and remember that.
Oh,
Okay.
sorry. How can I stop? Oh, there's a stop sharing. Okay.
Excellent. So I guess it's 9 o'clock, so we should get started. So everyone, good morning, evening, night, whatever it is for you. Welcome to the 3rd day of SAZERAC. So hopefully it's going to be another good day of talks. There's very few announcements. The only thing is I want to remind you that if you have questions after a talk, please ask them over Slack. And it's now also possible to do that anonymously. So if you in the Slack session type /anonymous, you can ask anonymous questions. So we'll just start off with Josephine Kerutt. Josephine, can you share your slides? And Josephine will be talking about searching for Lyman continuum in MUSE Lyman alpha emitters.
Yes, thank you very much. Okay. Okay. Hello, everyone. My name is Josephine Kerutt. I'm currently working at the University of Geneva, somewhere between finishing my PhD and postdoc. I'm working with Anne Ham and Pascal Oesch, and did my PhD in Potsdam with Lutz Wysocki. And I'm also part of the MUSE collaboration. So first of all, I want to thank the organizers for this very nice conference. I think it's a great idea to be able to share our science and discuss even in this difficult time. And also thank you for giving me the opportunity to talk here today. I will tell you about my project, searching for Lyman continuum emission and its connection to Lyman alpha emission using MUSE and the HDUV survey. So I guess for this audience, I don't have to advertise why Lyman continuum emission is interesting, but just to give you a reminder, of course, during the Epoch of Reionization, something has reionized the universe, and it's not quite clear yet what the contribution of galaxies to that is. Because unfortunately, Lyman continuum can't be directly observed at the Epoch of Reionization, only if you have very clear sight lines in the IGM, because it is absorbed in the IGM, of course. And the goal is to find some indirect tracers, for example, through the Lyman alpha line, to estimate the Lyman continuum emission through properties of the galaxies that can be observed up to very high redshifts. And several of these indirect tracers have been proposed in models already, for example, by Baham et al. But also some have been directly observed at lower redshifts, for example, in Isotoph, which you can see here. I think this has already been shown in this conference many times. So there is a connection between, for example, the Lyman continuum escape fraction and the O3 to O2 ratio, but also between the Lyman continuum escape fraction and the peak separation of the Lyman alpha doublet. So this is what I'm going to focus on. I want to find the connection between the Lyman alpha and the Lyman continuum. So the goal of this project is also to look for individual Lyman continuum Nika candidates and in the HDV data to find a connection between Lyman alpha and Lyman continuum by stacking objects. And also I want to highlight that it's important to make a good selection of the objects for stacking, to only use the most promising objects that can actually increase the signal. Because there has been a study already early this year by Bian et Fan, who used the same data and also do stacking, but do not find a Lyman continuum signal in their stack. So what is the data that I'm using? I already said I use MUSE and HDUV, and I use the MUSE data to find the line alpha emitters. So as you know, MUSE is an integral field spectrograph at the VLT and has a field of view of 1 square arc-minutes. And the redshift range, or the wavelength range of MUSE allows us to find Lyman alpha emission in a redshift range between 2.9 to 6.7. And I'm using here data from 2 surveys that were done with the GTO team of MUSE, which is MUSE Deep and MUSE Wide. And we use a blind search for Lyman alpha emission, so no HST priors. But this also means that we find lots of objects that do not have an HST counterpart because they are very faint and only bright in Lyman alpha. And here you can see the footprint of the data that I'm using of MUSE Deep and MUSE Wide. These are the little squares, and the shaded area is the HDUV survey, and they overlap nicely. So from the MUSE data, I get the information on the position of the Lyman alpha emitters, on their redshift, and also I get the spectral information, so the information on the properties of the Lyman alpha line, which will be important later on. And so with this information, I can start to look for a Lyman continuum emission in the HDUV survey. And in this plot on the bottom here, you can see which bands I can use for this. So you have the redshift and the wavelength, and in the black line and the dashed line are the Lyman alpha position and the Lyman limit. So everything bluewards of the Lyman limit will be the Lyman continuum. As you can see, MUSE, here's the wavelength range of MUSE where we can find Lyman alpha, and the Lyman continuum can be found in the HDUE band 336 or also 275, but I'm focusing on the 336 band to detect the Lyman continuum emission. I also make a redshift cut for my selection because, as I already said, at higher redshift, the IGM is not very transparent for Lyman continuum emission, so I'm focusing on the redshift 3 to 4 here. The first result is that I find 6 individual Lyman continuum leaker candidates, which you can see here. So on top is the UV continuum band, which is the 814 band. And then here you have the Lyman continuum 336 and also 275. There's already been a study by Rohainaidu earlier who looked at a slightly lower redshift range, redshift of 2, and also found 6 Lyman continuum leaker candidates. So while this is very exciting, if we want to understand the connection between Lyman continuum and Lyman alpha, the sample is still not quite big enough. So now I'm also doing stacks of objects. We have lots of Lyman alpha emitters that we found in MUSE. But as I said, it's important to make a useful selection of objects in order to only use objects that can contribute signal to the stack. And this is what I'm doing with this plot here. So I'm showing the measured flux at 1500, so the UV continuum flux. And on the y-axis, the Lyman continuum limit over the UV continuum flux. So this means I assume that each of the objects is detected by one sigma signal. And this is the flux that would then contribute to the stack. And on the top here, you can see the axis for the blue line, which is significance. I'm adding up all objects starting from below. And you can see that the significance has actually a maximum. So if I stack more objects, the significance goes down again. So I'm only using the lower objects, which you can see here, up to the maximum, theoretical maximum of the significance in order to only use objects that contribute to the stack. So basically, the argument is if the object is already very faint in the UV continuum or even undetected, which we have lots of objects in MUSE, as I said, then it will also not be able to contribute to the Lyman continuum and only add noise. So I'm having 60 objects here for my sample to stack. And another thing that I have to keep in mind is, as I already mentioned, the IGM transmission. I am using 10,000 lines of sight from Inno et al. To do the IGM correction. And as you can see, while most lines have no transmission at all, there are some, especially at lower redshift, with still a high transmission in the IGM, which you can also see in this plot. Every of the gray dots is one of the 10,000 lines of sight, and even at redshifts above 3.5, there are some clearer lines of sight. So now to the stacking. As I said, I make a redshift cut. I also exclude objects with bright neighbors, and I mask the neighbors and hot pixels or cosmics, and use the selection that I just showed. And this is the result. You can see that in the 336 band, I actually do detect a signal with the selected objects that I have. The signal to noise is roughly 5 if I include the individual candidates, and 4 if I exclude the individual line continuum candidates. And here you can see as a comparison the UV continuum. So now how do we get an escape fraction from those stacks? First of all, I want to highlight that with a certain signal to noise that I measure, there's a broad distribution of possible underlying escape fractions. So to estimate this, I make models of objects by using the UV continuum that I measure and an intrinsic UV continuum to Lyman continuum ratio, which I get from models from Starburst 99. One example can be seen here in this plot. And then I assume a specific escape fraction in certain steps and add noise according to the 336 band, and also take the AGM into account. And then I do this 10,000 times with all the objects that I have, and always stack them and measure the signal to noise to see what the distribution would look like. And this you can see in this plot here. So here's the occurrence of escape fraction values over the escape fraction, and the different colors of the lines are the different signal to noise values that I measure in the stack. So what I want is to now be able to read from the signal to noise that I measure what the most likely underlying escape fraction for Lyman continuum would be. So you can see these two lines correspond to a signal to noise of 4 to 5. So the distribution is rather wide. So even with such a high signal to noise, there's a possibility that the escape fraction could be as low as 20%, but the most likely escape fraction would be around 80% for the selected objects. Now keep in mind that this is not the escape fraction for the whole sample of Lyman alpha emitters, but just for those that I selected, and also the escape fraction could still be lower than this. So now to the part that I mentioned before, I want to understand if the Lyman continuum emission is connected to Lyman alpha emission. And for this, I separate my sample into 2 different halves, the half with a high property and the half with a low property of the line. So properties like equivalent width, width of maximum, peak separation, and asymmetry. And what I find is that the stack with the half of the lower equivalent width has a slightly higher signal to noise, also with only single peaks, so very narrow peak separations, and with a rather large asymmetry, which means for lines that have a broader red wing. But you have to keep in mind that I'm taking the spectra from MUSE. So even if I say, okay, the stack with only single peaks has a higher signal to noise in the Lyman continuum, this could also mean that we just can't resolve the double peaks in the MUSE spectra, because if the separation is closer than 200 kilometers per second, it's not possible anymore to detect the double peaks. So this could be a reason for the signal here, which would fit well with the models. So this is my summary. As I said, I detected 6 individual Lyman continuum candidates. I am making a specific selection to only include objects in the stacks that would contribute to them. I find escape fraction compatible with 80%, and I find a higher signal to noise for the lower half of equivalent width, higher asymmetry, and for single peaks. And with this, I thank you for listening, and yeah, we'll take questions.
Okay. Thank you very much, Josephine. Yeah, we'll start with very few questions. Aswin Vijan asks, have you tried alternative SPS models for the intrinsic spectrum BPAS? Do you think that would make a difference?
Yes, definitely. So I have started to look at BPAS models because I think that in Starburst 99, the Lyman continuum is predicted not to be that strong. So I find a very high escape fraction. I think if I'm using VPAS models, this escape fraction would not be predicted so high if I'm using a different intrinsic ratio between the UV continuum and the Lyman continuum. But this is something that I'm going to investigate now, yes.
Okay. And then Valentina asks, is it possible that some of your candidates are lower redshift interlopers?
Yes, so this is why I still call them candidates. There, for example, these two here, which are detected in the 275 band, which is quite unlikely. So we would expect from the IGM transmission that not much would get through here. We did some tests with different MUSE depths to see how often there are superpositions or wrong classifications, and the ratio for this is actually really, really low. So of the 6 individual candidates, statistically 2 could be superpositions or wrong classifications, but definitely not all of them.
Okay, then one final quick question. Why is the stacked Lyman continuum image peak offset from the center? How do you treat offsets of Lyman continuum from the optical profile centers?
Yeah, that is something that has been troubling me a lot. So I have done several tests to check why there is an offset. So I can exclude that it's something that there's something wrong with the positions that I'm using, because if I stack lower redshift objects, there's no offset. I also did bootstrapping, but to make sure that it's not just a single object, or yeah, but the bootstrapping showed that the offset is quite persistent. So I have no idea. It could be chance alignment, or it could be that there are some, yeah, something in the data that produced that offset, but I have not yet found a reason for this, unfortunately.
Okay, well, thank you again for a very nice talk. So let's move on. Nichole, can you start sharing your screen? So our next speaker is Nichole Berry, and she's going to talk about chasing the epoch of reionization using 21 centimeter power spectrum analysis from the Murchison Widefield array.
Yes, thank you. So my name is Nichole Berry, and I'm a postdoctoral researcher at the University of Melbourne. And today I want to talk about trying to measure the epoch of reionization in a slightly different sense, in a slightly different study than mostly is what is being talked about at this conference. And in particular, I want to look at it with Australian instruments. So I'm sure you've seen this multiple times already, but this is just a summary slide of a variety of different studies that have gone into trying to measure the IGM neutral fraction as a function of redshift. And they range from quasar studies all the way through cosmic microwave background studies. But in general, these studies have 2 features to them. Sometimes they can be line of sight studies. So in particular for quasars, you're looking at a particular line of sight and how the neutral fraction is in that particular line of sight. Or you can have model dependency. So for example, for the cosmic microwave background tau measurement, that is actually model dependent on a dust mask. And there's been a lot of studies to try to reduce this, but there's still a lot of room for a type of study that is model independent and is more global to help give context to these other studies. And that in particular is the 21 centimeter line of the neutral hydrogen. So this is a simulation of the epoch of reionization by the Dragons team, Paul and Simon in particular. And you can see the neutral hydrogen in the red here, and the ionizing sources turning on at about redshift of 15, all the way through about a redshift of 6. And as these ionizing sources ionize the surrounding neutral hydrogen, it dissipates. So if you're looking for the 21 centimeter line, you can actually look at a variety of different frequencies and make a movie of the universe as it's evolving through its last phase change. And you can also probe a lot of cosmological parameters in addition to the astrophysical parameters of the first sources themselves. So this is a GIF of a simulation done by Bradley Gregg and Jae-Hong Park of the types of parameters you can probe using the power spectrum of that 21 centimeter line. So they're just varying 8 different parameters and showing how that changes the absorption and the emission of the 21 centimeter line. And if I take a snapshot of a very typical model universe, on the top panel here, you have the universe slice as a function of frequency for the 21 centimeter line. So by the time the 21 centimeter line gets to Earth, it's in the radio frequencies, about 200 megahertz through to 60. And in the middle panel, you have the brightness temperature of that line relative to the background. And so you have an absorption feature and an emission feature. And on the bottom, you have the power relative to the background. And you can see that there's some fluctuations and some a lot of cosmological parameters you can probe just by looking at this one line. And it's at roughly about 10 millikelvin squared. But that's really faint. And so to put this into perspective, I'm going to give an analogy. It's like trying to measure a light bulb on Pluto in the middle of a lit stadium. And this is because not only is the 21 centimeter line very faint, but it's in the radio spectrum. And so all of the radio synchrotron sources between us and the Epoch of Reionization are extremely bright and drown out that signal. But they have a smooth spectrum, whereas the 21 centimeter spectrum is varying as a function of frequency. And so what you can do is you can take a Fourier transform and naturally separate these signals from one another. So on the left here, we have a power spectrum. This is the type of plot I'll be showing today. And on the x-axis, you have spatial scales. So left would be larger bubbles, larger imprints, and to the right would be smaller. And the more power you have in a specific K-bin indicates the size distribution of that bubble in the early universe. And there's a whole lot of different instrumentation around the world that's trying to measure this 21 centimeter signal. And in particular, I use the Murchison Widefield array, or the MWA, in Western Australia. And there's 2 main systematics that we have to be aware of in trying to make this power spectra. You can group them into analysis or observational systematics. Analysis systematics come from the pipeline, and there's a lot of bells and whistles to pipelines. This is just a very typical pipeline setup with a variety of different modules, if you will. And I want to, in particular, pick out these modules because we make a matched simulation with these modules for every single data analysis that we do. It's completely noiseless and it's full of foregrounds. And what you're looking at with this particular power spectrum is a theoretical EOR signal in brown and the simulation in blue. And so what you want out of your simulation is for it to be lower than the actual EOR signal, because the simulation traces out the systematics that you see. If it were perfect, theoretically, that blue line would be at 0. So you can see with this simulation, which was done in 2016, that we couldn't even theoretically detect the EOR. But over the course of 3 years, we improved our analysis greatly such that we could theoretically detect the EOR, which is definitely a good first step. And I don't have a lot of time to talk about these changes, but the main takeaway from all of them is that you need to have 1 part in 10 to the 5 spectral precision to hit that level of systematics. On the observational side of things, This is looking up at, from the MWA over the course of a few seconds. Mike Walensky found this object, and we don't know what it is. It's not aliens, at least we don't think so. We don't actually know what it is, but given the spectral signature of this signal, it appears to be digital TV channel 6 being reflected off a bottom of a bush plane from Perth, which is a town about 500 miles away. So that just kind of gives you the scale of the RFI mitigation that we need to perform. So this is what the field looked like at the end of 2019. Again, power spectrum, power as a function of K, with a variety of different publications and their redshift shown in color. And I want to point out a particular one. So we took Beardsley 2016 data here in the bow ties, that same exact data set. We re-reduced it with all of our improved analysis systematics. And we also removed as much of that channel 6 as possible. And then you get this solid line for Berry 2019. And that was an improvement of about a factor of 10. And then fast forward to today, 2 more papers came out that are further improving upon that limit. And in particular, I want to point out Mertens 2020, which is a LOFAR paper, a different instrument. They also improved by about a factor of 10. So we're all improving at roughly the same rate. But we're still orders of magnitude away from the EOR signal, as you can see here. However, we're starting to get to a regime where we can rule out certain models of the Epoch of Reionization. In particular, LOFAR and the MWA are very complementary because they're taking data at different redshifts. And so together you can use them to disfavor a wide variety, wide class of models. So they both disfavor cold reionization. They also disfavor soft band X-ray luminosities, below about 10 to the 38. And so if you're interested in learning more about these constraints, you can look at Greg et al. 2020 and his upcoming other paper as well. So in summary, the 21 centimeter power spectrum analysis is a global model independent study, which hopefully can give context to all the other EOR studies out there. However, it's difficult because it needs to be extremely spectrally precise and have extremely high RFI mitigation. However, we are starting to rule out some extreme reionization models, and it'll be a good space to pay attention to as we start to lower those limits and rule out other models as well. And so with that, I'll take questions.
Okay, thank you very much, Nichole. So a few quick questions. Anonymous says, what do you think we can ultimately learn before the arrival of full SKA?
For the SKA?
Before, what can we learn before?
Yeah. Right now, what we're attempting to do is just get a measurement of the power spectrum itself. This might just be a one-off measurement using our best frequency band. So that would be a measurement of 1 redshift. So it would kind of just give a benchmark for the SKA, I would say, and that's what we're hoping for at the moment. And of course, with the SKA, we would hope to go even further, maybe even one day image the 21 centimeter signal. Okay,
I had one question myself. So you've just very impressively improved the pipeline with a factor of 10. Still need quite a few. Where's the next sort of factor of 10 coming from? Like if you look at that, all those steps that you outlined, what is the most likely thing to give you another order of magnitude?
Right. So some recent work I've been working on is to avoid taking an FFT at any point. because whenever you take an FFT, you get aliasing. Whilst it's quick, it doesn't quite have the precision that we need. And so I've been trying to move towards a model of using Gaussians or other analytic Fourier transforms to do the same things, to give us the same results, but without that aliasing.
Okay. Another question, do MWA and LOFR constrain the lower limits of the IGM temperature?
Not at this point. And it might be a while before we get to that. Right now, we're just doing extreme models.
Okay. And a question, how will you verify a detection? Cross correlations?
Yeah, that's an extremely difficult question, and one that I've had before. At the moment, it's not necessarily the biggest concern of ours to because we're just so far away from actual detection. But I think that no matter what we do, the only way that you can actually confirm a detection is to detect it once with an instrument and detect it again with a completely different instrument on the other side of the planet.
Okay. And then final question, how do the current constraints compare with original predictions for the experiments? Have you done better, worse than expected so far?
We've done worse. So it's been quite a learning experience, and I think this was really important to do before SKA came around. There were a lot of systematics that were inherent to the measurement itself that we cannot disentangle ourselves from, that we didn't know were there until we looked at the data for the first time and we're like, what is this? For example, there's a chromaticity that gets convolved into your data via the instrument itself, due to the fact that the spacings between your interferometric elements vary as a function of frequency. And that variation as a function of frequency, as soon as you take a Fourier transform, contaminates your signal. And so for the most part, these instruments have been a learning experience. And to be honest, I think a lot of people who first proposed for these instruments thought we would have measured it within a couple of years.
All right. Well, we should move on. Thank you again for a very nice talk. Mathieu, can you maybe start sharing your screen? Mathieu, are you online? Okay. If we're having some technical problem, Laurent, could you step in and quickly switch with Mathieu and start sharing your screen?
Yes. Wait, can you see me? Can you hear me?
Yes, I can see you. Yeah.
Oh, okay.
So Laurent Legrand is going to talk about quantifying the star formation history of the Epoch of Reionization.
Yes, indeed. Hi, everyone. My name is Laurent Legrand, and I'm currently a PhD student at the Kaptein Institute in the Netherlands, working with Pratika Dayal and Anne Hutter mainly. And here I would like to show you the work I've been doing on quantifying the star formation history during the Epoch of Reionization with the collaborators you see here. So the past 2 days have actually been the best introduction for my project, as we've seen that LCD fitting has been used a lot, is used a lot, and that one of the important parameters that goes in it is the star formation history. And this allows us to derive a variety of properties for high redshift galaxies, such as the stellar mass or the star formation rate or the metallicity. However, we've seen that multiple forms of the star formation history, such as constant or rising, mainly for now we've seen, have been used because we can only measure the star formation history of some local galaxies. So what we want to do here is provide a prescription for the star formation history of these galaxies. So our model starts with an n-body simulation, the very small multi-dark plank within the multi-dark project, which has box size of 160 H inverse megaparsec, so quite a big box for what we're trying to do here. And we have a mass resolution of 6.2 10 to the 6 H inverse solar masses, which makes it so we can study halos of 6.2 10 to the 8 H inverse solar masses. And through the phase space halo finder, Rockstar, we trace here the different halos across redshift, and we can extract merger trees here that allows us to apply our framework. So here you can see the first halos that collapse and they merge until the one at the last redshift. So now I can show you Astreus, our new framework. So these first halos that collapse, when they do, there is a galaxy inside of them that form and that have a certain amount of gas. And within this gas, star formation happens. And the first feedback we include in our model is the supernova feedback. So the stars that are big enough end of their life as type 2 supernova that deposit energy in the gas and expel some of the gas. If the galaxy is small enough, as a small gravitational potential well, then it can eject all of the gas, quenching further star formation. Then we can follow the evolution of these galaxies, and when they merge, they just give all the remaining gas and stars to their descendant. Here you can see that the descendant has more gas than the combined progenitors, because we also have accretion at the cosmological ratio. So when dark matter is accreted, gas is accreted as well. And finally, the second and last feedback we include is reionization feedback that first reduces the amount of gas that is accreted and photoevaporates some of the gas of the galaxy, reducing the star formation. We show here two reionization feedback model. The photoionization, which has in intermediate time delayed weak radiative feedback, and the Jeans mass, which is instantaneous and a very strong feedback. And so on and so forth. The galaxy just starts forming stars, and supernova feedback happen, and more mergers and accretion. So now, as first quick result here, I showed the halo mass, gas mass, stellar mass, and star formation rate of galaxies of increasing stellar masses. And we can see that for the star formation rate, as a function of redshift, so the star formation history, the slope increases with stellar mass already, as I will show later as well. But here, what I want you to look at is at the stochasticity. So we can see that for the low mass galaxies, the star formation history is very stochastic. And when the star formation history goes out of this region between the two black lines, we assume that the galaxies is stochastic. So for example, here from the beginning, it's stochastic. But when you go to higher stellar mass, then you can see that the star formation history is more well behaved. So now we can look at exactly how this stochasticity, and lastly, we choose then to model the star formation history as constantly rising. And now we can look at the stochasticity as a function of mass here on the y-axis and redshift. And here is the total fraction of stellar mass that is locked in stochastic regime. And we can see that it decreases with stellar mass and it increases with decreasing redshift. And these two effects are both due to the gravitational potential of galaxies that become shallower towards lower mass and at lower redshift. And so they are not able to retain their gas against supernova feedback and then radiative feedback as well. That here you can see that photoionization takes some time to impact the galaxies, while the Jeans mass directly slightly increases the stochasticity in low mass galaxies. We don't expect the high mass galaxies to be impacted for these parameters because they have a strong enough, deep enough potential well to keep their gas against radiative feedback. Now, secondly, we will show a fit of alpha and beta on the slope and the normalization of the star formation history. But another interesting property is the mass at which galaxies escape this stochastic regime. So goes from being stochastic star formers to continuous star formers. And here we can see that for the same reason as before, the amount of mass that is formed in a stochastic way, so the transition mass decreases with stellar mass and increases with redshift. But now, an additional effect is that as the radiative feedback becomes stronger, this transitional mass increases even for massive galaxies, because the Jeans mass model has immediately a very strong impact on galaxies. So in their history, they need to have a higher mass to retain their gas and start being continuous star formers. So here I would like to show you the fit that we've done of the star formation histories. So first, the slope. Here I remind you of how we model the star formation history. And on the slope, you can see that as soon as star formation in the galaxy becomes non-stochastic, so around here, let's say, its star formation rate rises continuously following the dark matter assembly. So here, it's not, the slope reaches a plateau, meaning that from that moment, the star formation rate rises always in the same way. And that with redshift, so here you can see redshift 10, this plateau is reached at a lower mass, as explained before, because at a higher redshift, then the gravitational potential of galaxies of the same mass is deeper than their counterpart. And for the Jeans mass model is about the same plateau here. Now, secondly, we have beta, so the normalization of the star formation history, which is a proxy for the gas reservoir when reaching continuous star formation. And we can see that it, again, increases with redshift and with stellar mass as well. So now we have the fit of the star formation history, as well as the transition point from which this fit is correctly reproducing the star formation history, like very accurately. And we can use that to check, and we can check if it gives good results. So using this continuously rising star formation history, we see that we can recover the stellar mass functions here. So the number density of galaxies of a specific mass. For a redshift from 10 to 5, we recovered this stellar mass function quite well. So as a summary, using our new framework, we quantify the star formation history of the galaxies and the transition point. And the feedback mechanism we include delays this transition point to either a later time or higher mass. We have found a fit for the continuously rising part of the star formation history, which allows us to recover the stellar mass functions when we use them. Thank you for your attention.
Okay, thank you, Laurent, very much. Let's see if there are questions. While people are typing, I'll ask a question. So as an observer, I'm always interested in what the star formation history means, for example, for the emission lines that you might be able to observe, how you can verify that. Do you have any plans of making predictions for what you can see with JWST, and what can we already, how can we use your model now to look at the emission lines that we see with, for example, Spitzer?
No, I haven't yet planned on using the model that way. Our next project is also working on the stellar mass, the star formation history, and how it evolves with the overdensity that the galaxy is sitting in. But it would be very interesting to look at the emission lines that this fit would give.
Okay, so another question is, I'm not sure if you showed this, but is there any figure where you show the proportion of all star formation in stochastic mode?
The proportion of all, sorry, the proportion of all star formation?
All stars that are formed in stochastic fluctuation.
No, I haven't showed that. I mean, the closest I have is this plot that shows, but I can easily recover that from this plot and I mean, we can also get it from the critical stellar mass if we also have the number density of galaxies at each redshift and stellar mass.
Okay.
But I don't know which information we would get.
All right, I'll go on to the next question. How is the evolution of Jean's mass parameterized here? Is it a function of metallicity?
The Jean's mass have been done. There is the first paper in the series, so Asteroid 1 by Anne Utter, that shows how the Jean's mass is computed. But here metallicity doesn't play a role.
Okay. How do your star formation histories compare to the traditionally used ones in terms of deriving, say, M star? In other words, how well badly do you do when you assume a traditional star formation history?
I haven't compared my star formation. I just did this validation for now, but I haven't compared with traditional assumed star formation histories.
You know, when you do SED fitting, people use these in constant star formation history or exponentially declining, or so yeah, you have some information on how badly those assumptions are.
No, I haven't now, because here it's very obvious from the star formation histories that we recover that it's not constant but continuously rising. So if I don't know how it would fit a constant or bursty star formation history here.
Okay. Okay, well, let's move on to the next talk. We're gonna try again. Thank you again, Laurent, for a nice talk. I'm gonna get Mathieu in, who's had a little bit of connection problem.
Yeah, it seems to work now.
Okay, that's much
Sorry
better.
for the reorganization I just created.
No, that's fine.
Yeah,
okay.
It just froze at the worst time. It was perfect.
A nightmare scenario.
Yeah, I mean, the timing was absolutely perfect. Anyway. Okay, so thanks for having me today first. And so I will talk about characterizing the sources of reionization in SPHINX, which is my PhD that I'm doing with Jérémy Blaiseau at the CRAL, so in Lyon in France. So first, few words about the sources of reionization. So they're supposed to be, even if there is some debate, they're supposed to be the galaxies according to both observation, but also according to simulations. And for example, in SPHINX, we use only the galaxies as a source of reionization. And as you can see on the graph, our simulation reionized by redshift 6, and it matches pretty well the observation if we use the binary model for the star formation. So a few words about the SPHINX simulation. If you want full description, you can find it in Rosdahl et al. 2018. But so it's a cosmological simulation which uses a Ramsey 30, which is an hydrodynamical AMR code. And myself specifically, I work on a 10 co-moving megaparsec box with a resolution of 10 parsec at redshift 6, a dark matter resolution around 10 to 5 solar masses, and a stellar particle resolution around 10 to 3 solar masses. So to characterize a source, so a galaxy of reionization, you need to wonder about many things. You need to wonder about the directionality. Do your photon escape in one direction or in all directions? And you need to wonder when the source is on, when the source is visible. So it will depend on the intrinsic luminosity of the source, of course, but also on the escape fraction. You can have a bright source, but totally opaque. And on the duty cycle, sometimes the source is, a same source can be totally opaque and totally visible. In fact, it's like characterizing a lighthouse. And the main goal of this study is, of course, to understand the process of reionization, but also for bigger simulation where the galaxies are not resolved, so they need the work of simulation where the galaxies are resolved. So in this talk, I will specifically focus on the spatial evolution of the escape fraction, so the directionality, and the time evolution of the escape fraction, so the duty cycle. First, I will talk about the time evolution of the escape fraction, and I will focus on one case, which is the most massive case. But briefly, I will first show the distribution of the escape fraction as a function of the virial mass for all halos. What I mean by all halos is all halos I studied, so at all redshifts between 12 and 6. And you can see in this distribution, you have quite a complex distribution with a lot of halos with no escape fraction, another important population of halo with a full escape fraction, and the rest of the halo distributed more or less equally between these two extreme values. So it suggests a duty cycle associated with feedback. And in fact, if you add the FSK evolution of the most massive halo, so in red, you see that there is a correspondence between the distribution, the global distribution, so in gray in the background, and the FSK evolution of the most massive halo with the presence of a duty cycle. And also you can see that both the global distribution and the escape fraction for the most massive halo are decreasing at high mass, sorry. And so you can wonder, first, why do we have a duty cycle? What are the reasons for this? And why do the FS peaks decrease with the mass? So to understand this process, I studied different peaks of escape fraction for the most massive halo case, and I studied the beginning, the top, and the end of the peak. And I plot on the top the neutral gas of the halo with overplotted the brightest stars, because since the escape fraction is luminosity weighted, they are the stellar particles that drive the escape fraction, in fact. And in the bottom, I plot the escape fraction as a function of the age for all stellar particles inside the halo, with the luminosity of the stellar particle color-coded. And in fact, you can see that we have a feedback-regulated escape fraction, and you can find more detail about this in Trebich et al. 2017, because at the beginning, the stellar particles are very bright, but with no escape fraction, because they are just born in a dense neutral environment. But then at the top of the peak, you see that this stellar particle has a huge escape fraction, because if you look at the map on the top, they totally, with the feedback, blow away and reionize the environment, so the photon can escape, and the global escape fraction increase. And then this stellar particle become less luminous, and the gas will be reaccreted and become neutral again, so the escape fraction will decrease. So that's the story for a big peak of escape fraction. But if you look at higher masses, so a small peak of escape fraction, you can see that you have a similar story locally, like you start with a very bright population of stellar particles with no escape fraction, and locally, after a few megayears, these stellar particles succeed in, with the feedback, in reionizing their environment and increasing their own escape fraction. But the difference is with before is that you always have an ongoing stellar formation. At all output, you can see that you have very bright young generation of stars with no escape fraction, with totally counterbalance, in fact, the stars with high escape fraction, and drives down the escape fraction. And even if locally you can have a high escape fraction, the total integrated escape fraction will be always very low, in fact. And you can see that also on the map. You see that the region where stars are formed is always very dense and always very active. So to sum up briefly this first result, at low mass, before a new stellar population appears, the dominant one in terms of luminosity has time to create a H2 channel, and you can reach a high escape fraction. But at high mass, even if locally you can have a high escape fraction, the integrated escape fraction is always very low because of the ongoing star formation. So on the second part of the talk, I will talk about the observability of the escape fraction. So first, in the SPHINX simulation, as in fact in many simulations, we can see that the photons are escaping in an anisotropic way from halos. So as it is illustrated on this schematic, for example. And also another interesting point is that for the most massive halos, because they are more resistant to feedback, they tend to have a lower solid angle to reach photon escape, because it's impossible to totally clear away and blow away a massive halo. But once you know that your photons escape in an anisotropic way, you can wonder what will observe, an observer. Because it's easy to understand that if you look at one galaxy from at a group of galaxies through one direction, the brightest source you observe may not be the actual brightest source if you take into account all the direction. There may be a difference between the FS1D, so which is the FS fraction you measure through one direction, and the FS3D, which is the escape fraction you calculate if you take into account all the direction. And so the question is, okay, can I estimate the 3D escape fraction if I look at a group of galaxies only through one direction, so with FS1D? So I try to answer this question. And for that, I took the most massive halos of my simulation, so halos above 10 to the 9 solar masses, and I mocked the observation of n galaxies to see if I can estimate the 3D escape fraction. And I did that for different numbers of galaxies. So I did that for 10 galaxies, 100, and 1000. And I plot the distribution of the measurement of FS1D. And what is interesting is that no matter the number of galaxies, so from 10 to 1000, the distribution of the measurement of FS1D always peaked at the expected 3D value. And to be more precise, if you calculate the average of the distribution, so in red, you always find the same values that the average 3D value for the same group of halo. So this means that there is no bias. With FS1D, you can measure the 3D escape fraction. But so the question, once you know that, is, okay, I can measure it, but how precisely can I measure this? And so to illustrate that, I did the same plot, so the distribution of FS1D, but in cumulative. And so I represent here it for 100 halos. And you can see that, in fact, the measurement is pretty precise. Like for 100 galaxies, you have 60% of chance to be between 0.6 FS3D, so the expected value, so one you want to measure, and 1.2 FS3D. And another interesting point is that the median is quite low compared to the FS3D value that you can see here in red. And which means that for a group of galaxies you target, you will have a tendency to underestimate, in fact, FS3D. So I will leave you, I guess I'm around 10 minutes, so I will leave you with the conclusion. And in fact, one of the big prospects for my future studies to do the same works, but with a bigger simulation with 20 co-moving megaparsec aside, and it will help me to increase my mass range study and to go to higher mass range around 10 to 10 and 10 to 11 solar masses.
Okay, thank you, Mathieu, very much for that nice talk. So let's see some questions. So Tom Tens asks, bursty star formation may leave an imprint in the abundance pattern of extremely metal poor stars when metal mixing is not efficient. Have you looked at this?
Have you looked at what? Sorry, I didn't hear.
Bursty star formation may leave an imprint in the metal in the abundance pattern of extremely metal poor stars when metal mixing is not efficient?
Sorry, I didn't hear properly. I'm gonna look at it. Oh, okay, I'm reading the question. No, we didn't have a look at it, sorry, for now. But so yeah, maybe. No, I didn't look at anything close to the metallicity yet. So it can be interesting for the future project. But for now, no, I didn't look at it.
Okay. Then Marisha Braddock asks, observations of Lyman alpha emitters and QSO seem to suggest a more rapid reionization than your simulations predict. First slide. This would maybe imply that massive galaxies have a higher F-escape. Do you have any thought on that?
Yeah, there is still some debate about when the reionization is happening. So yeah, we kind of first agreed that it was around redshift 6, but now yeah, there is, as she said, a debate about maybe it's earlier. And in the simulation, I quite miss massive halos, but for me, the massive halos has no specifically high escape fraction, and even many simulations find that more massive halos tend to have lower escape fraction because, as I said, they are more resistant to feedback. But specifically on my work, I'm quite trapped because I have only like 10 halos above 10 to the 10 solar masses. And that's one of the reasons we are switching to SPHINX20. It's because we want to increase this mass range above 10 to the 10 solar masses. And because, okay, we succeed in reionizing the universe thanks to our small galaxies, but maybe the more massive galaxies can play an important part. So we need to focus on that, and we hope SPHINX20 will bring more answers to this kind of question.
Okay. So final question, Jörg Mate asks, are you planning to produce Lyman alpha spectrum of simulated galaxies? And a related question, do you expect the Lyman alpha escape is similarly anisotropic as Lyman continuum escape?
That I think they will have a talk about this from a colleague. So me specifically, no, but I know some people that I work with in Geneva are focusing on this, and they are specifically focusing, so I don't want to spoil her talk because I think she will talk today. But yeah, she's working on the link between Lyman alpha and Lyman continuum and the spectrum also. And you can see that there is a link, like if you look at sky map of Lyman alpha and a sky map of Lyman continuum, they are highly correlated. So if Lyman continuum is anisotropic, there is a huge chance that for the same galaxy, your Lyman alpha will be anisotropic, and of course the other way around. They are highly correlated.
Okay, very nice. So we have a few more questions, but in order to keep on time, I suggest you go to Slack and answer them directly. Okay. All right. Well, thank you very much, Mathieu, for a very nice talk. Yongjung, can you maybe start sharing your slides?
Okay, I'll share my screen. Yep. Can you see the?
Yeah, I can see. I hear you.
Okay, got it.
Make it full screen though.
Okay. So.
Yes, very good.
Yep. Hello everyone. Yeah, my name is Yongjung Kim, a KIA fellow at Peking University, China. Started last November. First of all, I greatly thank the SOC and other members for giving me this kind of great chance in the current pandemic situation. And today, I'll give a talk about the Quasar luminosity function at redshift 5 with the infrared medium deep survey, shortly IMS. This work is related to my PhD thesis and was submitted to APJ and under the revision now. Now it has been widely known that the intergalactic medium, or IGM, has been almost completely ionized after redshift 6. As shown in this figure, the neutral fraction dramatically dropped at around redshift 6. But it was debated that what ionizing sources can maintain the ionization state of the IGM in the post-reionization epoch. quasars radiate a huge amount of UV photons by accreting the materials into their central supermassive black holes. So they are regarded as a potential contributors. The right figure shows the redshift evolution of UV emissivity from quasars, and as you can see, there are large scatter at high redshifts, which makes it difficult to determine the quasar's role in to ionize the full IgM or not. The reason for the large scatter in emissivity is mainly because of the lack of faint quasars, especially at -23 or -24 magnitudes, absolute magnitude, yeah. And this figure shows the differential emissivity distribution as a function of the magnitude derived from the recent quasar luminosity functions at redshift 5. And as you can see, the emissivity efficiency peaks at around -23, 24 something. But unfortunately, due to the survey limitation, the number density of quasars in this magnitude range was uncertain yet. The right figure shows the quasar luminosity function. I showed the QLF here at the QLF at redshift 5, and except for the Jianan Li et al. In 2019, shown as some purple line, it seems that their parametric QLFs, shown as the solid lines, are in line with each other's. But as I marked, each study has its own limitations, such as some survey depths, biased sample, or some limitation to some parameterization, and so on. So here we try to derive better QLFs at redshift 5 by finding more faint quasars. Recently, our group have performed the infrared medium deep survey, shortly IMS, which is the NIL imaging survey. The imaging data in Y and J bands were obtained with the Widefield camera on Kerutt, and IMS covers over 100 square degree area on the sky and reaches the J band magnitudes of 23 in AV system. This kind of the imaging depth is appropriate to fill the deficiency of the faint quasars. So including the optical imaging data from CFHD legacy survey, we have performed high redshift quasar survey with IMS. The combination of these optical and NIL imaging data enables us to find faint quasars down to -23 magnitude at redshift larger than 5. In this presentation, I'll give a talk about the quasars at around the redshift 5. The red color from the sharp line alpha break is a key to find the high redshift quasars. So the broadband color selection method have been well established. And we initially selected 69 quasar candidates with broadband colors. Unfortunately, the dwarf stars also have similar red colors and can be interloopers. So we introduced the medium band filters, which have only 500 Armstrong bandwidth, and which allows us to obtain finer SEDs, like some kind of the low resolution spectroscopy. And this figure shows that it's efficient well. As you can see in the top panel, the higher quasars colors are similar to the dwarf stars in broadband, but if we use the medium band colors, it is expected that we can easily distinguish the break of the higher quasars from the dwarf stars red colors. On this medium band color diagram, we successfully narrowed down the number of the plausible candidates for some redshift 5 quasars. For the plausible candidates, including the broadband salty or the medium band salty candidates, their spectra were obtained with the large telescopes, such as the Gemini 8-meter telescopes or some Magellan 6.5-meter telescope. And we already published 13 quasars in 2019, and here also identified some 8 new quasars. And consequently, we identified 21 faint quasars at redshift 5, while 18 of them are newly discovered ones. We include additional 22 quasars identified by previous works, which were also selected by our selection criteria. And in total, we have 43 spectroscopically identified quasars. Now we consider two cases for the case one for the broadband selection only and case two for the combination of the broadband and medium band selections. The number of quasars in each case are 43 and 32 respectively. And we calculate the quasar selection function in each case, as you can see in the right figure. Note that we use the improved version of the high-resolution quasar model in our previous work. Also, we consider the photometric and spectroscopic completeness of our survey, as shown in the right bottom figures. The combination of these two gives the total selection probability. Using the total selection probability P, we calculate the luminosity function at rest 5. First, we calculated the bin QLF using the well-known vulnerable BMAX method. The red and blue circles in the right figure are the bin QLF in case 1 and 2 respectively. And second, we calculate the double power shape quasar luminosity function QLF using maximum likelihood method, which are shown as the solid line with some shaded region of the 1 sigma confidence error, confidence level. And note that in this calculation, we include the bright SDSS quasars in Yang et al. In 2016, shown as the orange circles in this figure. And in this work, we, for the first time, derived the parametric QLF down to -23 magnitude without any fixed parameters, and with some very flat faint slope of -1.3. The QLFs in the both cases, case 1 and case 2, I mean, are consistent with each other. And considering the high success rate of our medium band selection, as we published before, especially at the faint magnitudes, wide area surveying medium bands will allow us to estimate the reliable QLFs at high redshifts, even without deep spectroscopic observations. When we compare our QLF with others, it shows some flatter faint slope of -1.3, as I mentioned, while the other studies suggested -2 something, as you can see in this figure. But note that the values in Yang et al. And McGreal et al. Have their own limitations, as I mentioned. And interestingly, our value of -1.3 is similar to recent HSC quasar surveys at redshift 4 and 6. Our QLFs are consistent with the most. It's very interesting and currently is in working. Yeah, sorry. And our QLFs are consistent with the most of the QLFs in previous works, as you can see in this figure, except for some Jianan Li in 2019, shown as the purple line. At around -24 magnitude, they used the bin QLF from the small area surveys and covering only a few square degrees. So we can say that compared to the Widefield area survey, we can say that their estimation in this magnitude range can be overestimated due to some kind of the serendipitous detections. At magnitude fainter than -23, Jianan Li's QLFs relies on the very faint X-ray quasars. But so we can think that the one possible explanation for this discrepancy between ours and Jianan Li's is due to the high fraction of the UV obscured quasars at redshift 5. But we note that the recent X-ray QLFs corrected by Shen et al. In 2020 show a good agreement with our results. We also calculate the UV emissivity by quasars under the several assumptions. Despite the extrapolation of our QLF at magnitude fainter than the -23, the emissivity efficiency at that magnitude is insignificant with our QLF. So we estimate the emissivity down to -8 in magnitude, and the observed emissivity is shown as the red circles on the right figure. And this value is the lowest value at redshift 5. However, when we consider the results from the large area surveys shown as some kind of field circles, all the points are in line with the model of the Hartland model in 2012 and other empirical models shown here as well. We also calculated the ionizing photon density by quasars, assuming the escape fraction of unity and Doppler shape of the UV quasar spectra. And we compare this with the critical density required to fully ionize IgM, shown as the gray thick lines and squares. And we suggest that only about 10 or 20% of the UV photons are from quasars. And it is up to 50% even in the extreme case. Therefore, we discredit that the quasars alone could provide UV photons enough to keep the ionization state of the IgM in the post-reionization epoch. So here's the summary of my talk, and feel free to ask your questions in Slack. And after this work to be posted on archive soon, and thank you for your listening.
Thank you very much, Yongjung. So we have a couple of questions. First of all, how did you calculate the 1 sigma envelope on the maximum likelihood luminosity function?
Yeah, wait a second. Yeah, maybe meaning this kind of the confidence level, and as you know, it is well known that using the maximum likelihood and the factor S, you can calculate the it can be approximated to some kind of the chi-square distribution. So on the this parametric distribution of the S, we calculate the 1 sigma confidence level for this parametric QRF.
Okay. And another question is, could the flatter slope be due to the completeness corrections applied by yourself and others compared to what others have shown?
I'm sorry, could you?
Could there be a difference in the slope between your luminosity function and other works because of the completeness, because of different assumptions on the completeness correction?
Yeah, it might be, but actually the method to calculate the completeness and the other thing is just, I think that it's very consistent with each other. So yeah. Okay. So I think it's not a critical thing, but yeah, but for the some kind of small survey area, the completeness and some selection function might be important, and we think that the values that being the QLF from the small surveys might be overestimated. Yeah, so
okay,
but it's important to regarding the completeness issue.
And then another question: is there any prospect to follow up your sources in X-ray?
Any prospect for X-ray sources?
Yeah, are you going to follow up your observations with X-ray observations, or is there any possibility that you could do so?
Yeah, but you know, the X-ray observation is not easily accessible, and also yeah, but yeah, of course, then maybe there's some kind of the follow the Widefield X-ray surveys required for the see this this kind of the discrepancy and solve the problem between them. But yeah, actually, I have no idea right now. It's good to think of it.
Okay. There are a few more questions on Slack, but in order to keep on time, I propose we move on, but please do answer the questions on Slack.
Yeah, thank you very much.
So yeah, thanks again for a really nice talk. And so
I'll stop the share.
Okay. Jianan, can you use your slide? So Jianan Li will talk about probing the physical conditions of the interstellar medium in the most distant quasar host galaxies.
Mm-hmm. So can you see my screen and can you hear me?
Yes, both. Excellent.
Okay. So hello everyone, I'm Jianan Li, a graduate student from Peking University in China. And today I'll talk about the molecular, ionized, and atomic interstellar medium in a particular redshift 6 quasar, the SDSS J2310. So we have already know that observations of the quasars at the highest redshift are essential for our understanding of the coevolution between the supermassive black holes and the host galaxies, especially the observations of the interstellar medium at redshift 6, because the interstellar medium are directly exposed to the radiation field of the both the UV photons from star formation and the radiation field produced by the very luminous quasars. So studying the physical conditions of this interstellar medium will also help on our understanding of the coevolution. So these studies are basically through observations of the CNO fine structure lines and also the sub-millimeter CO transition lines. And these lines are easily accessible by ARMA, NOEMA, and VLA at Redshift 6. And through these observations, our objectives are to find if there is a typical ISM physical conditions for this Redshift 6 quasars and how is it compared to local starburst systems and AGNs. And also, are we able to discriminate between different ISM heating mechanisms, like the UV heating, which is produced by the stars, and S3 heating, which is mainly produced by the AGNs. So then we start a case study of one of the far infrared brightest quasar, J2310 at Redshift 6. So this quasar is very interesting, and it has been detected in the low CO transition to mid-J CO transitions, and the C+ line, and also the oxygen 388 micron. So in this talk, I will briefly introduce our ARMA and NOEMA observations of the molecular CO lines and water emissions, and this has been published in LAE 2020, and we also include the fine structure line observations, and this is our ongoing work. So actually, our new CO observations are covering J equals 5 to 13, and in complemented with previous CO2 to 1 data, we are actually probing the CO from J equals 2 to 13. So now I will introduce the physical conditions of the molecular gas probed by the CO slide analysis. So the CO spectral line energy distribution is shown in this plot. So it's the CO flux as a function of the rotation quantum number J. So this shape of the CO slide change with both different density for fixed temperature and also different temperature for fixed density. So these are ideal probe of the temperature and density of the molecular gas. So currently there are only 4 published CO slides for Redshift 6 quasars with at least 4 transitions, so which enable us to do the CO slide analysis. And the above 3 panels are result from previous work, and this is our result for this J2310 quasar. So if we use one gas component to feed the data, we get warm and dense gas component with temperature of around 228 Kelvin and molecular hydrogen density of 10 to the 4.75 per cubic centimeter. And if we use 2 models to feed the data, we get a cold component in blue with a temperature of 50 Kelvin and a warm component with a temperature of around 300 Kelvin. So we find that all these different quasars with CO slide detections have different shapes of the CO slide. But it seems to be there is a universal warm and dense component which dominate at the high J CO transitions. So what is the heating mechanism of this highly excited CO component? We then compare the CO slide of this quasar in black with the local ULERC and starburst galaxies and also the high redshift sub-millimeter galaxies. We find that this quasar show high CO excitation at J equals 8 and above compared to these starburst systems. And we also compare this quasar with local representative starburst galaxy and AGNs. We find also that higher CO excitation for this quasar compared to the local examples. And here is the CO slide comparison with other Redshift 6 quasars and also the Redshift 224 lensed quasars. We find that this quasar has a CO slide among this high redshift and lensed quasars. So the high CO excitation compared to the local and high redshift starburst systems may reflect that there are other mechanisms besides the UV heating from young massive stars. maybe the AGN also contributes to the heating to the molecular ISM. And then I will introduce the neutron and ionized ISM observations. That there are many observations of the nitrogen-2 122 micron and also the oxygen-1 150 and 46 micron, which probe the neutron gas and the ionized gas. So the y-axis is the line to far infrared ratio, and the axis include the far infrared luminosity for these two panels, and the far infrared surface brightness for these lower two panels. So for the nitrogen-2 line, this dots with no error bars are local dwarf galaxies, ULERCs, star-forming galaxies, and AGNs. And this with error bars are high redshift sub-millimeter galaxies and quasars. And so this quasar generally follow the trend of the local relation. And also we find that in the far infrared surface brightness plot, all of these high redshift objects lie within the deficit trend of the nitrogen-2 to far infrared ratio. As for the oxygen-1 line, this is the far infrared surface brightness. We find that all of these high redshift objects are above the relation set by the local samples. So this suggests that we actually find similar line deficit trend in the nitrogen-2 line, but there's no sign of oxygen-1 deficit. And from our new observations of the ionized and neutron gas complemented with previous C+ and oxygen-3 line, we are able to use these line ratios to probe the physical conditions of the neutron and ionized gas. So this plot, the y-axis shows the luminosity ratio of the C2 to oxygen-1 line, and the x-axis is the oxygen-3 to nitrogen-2 line. So for the C2 to oxygen-3 ratio, we find that this quasar together with other two high redshift objects lie on the lowest C2 to O1 ratio compared to the comparison samples. And the low C2 to O1 ratio are indicator of warm and dense gas. This together with the very high oxygen-1 to far infrared ratio in this quasar suggests that the high warm and dense gas may be heated by the AGN. And here is the oxygen-3 to oxygen-1 line. This is a proxy of the ionized to neutron gas volume filling factor. So we find that this quasar has a lower volume filling factor, ionized volume filling factor compared to the mean of the local sample, and also compared to other two high redshift objects. And as for the oxygen-3 to nitrogen-2 ratio, we find that this quasar shows a comparable ratio with the mean of the local sample, and this is smaller than the other two high redshift objects. And from the nitrogen-2 line, we also derive that less than 17% of the C+ is from the ionized gas region. So this is also in agreement with the lower ionized gas fraction derived from the line ratio analysis. And because the oxygen-3 to nitrogen-2 line has a dependency on the metallicity, so this line can be used to estimate the metallicity. And from these two luminosities, we derive a metallicity of 0.5 to 2 times of the solar luminosity. This means that this redshift 6 quasar is already metal enriched with solar metallicity. And we also use this line luminosities to derive the star formation rate. And we find that except for this oxygen-1 line, the other lines have a reasonable estimation of the star formation rate. So here comes the summary. So our cell-slide analysis suggests the gas is dominated by a warm and dense component, and this is very universal for the redshift 6 quasars with CO slide detection. And these are probably signs of the AGN heating to the gas. And comparison of this quasar with other high redshift starbursts and local AGN suggests higher CO excitation. But this high CO excitation is also found in other redshift 6 quasars and lensed quasars. And through the fine structure line ratio analysis, we find a low C2 to O1 ratio together with the high oxygen 1 to 5 infrared ratio reveal a warm dense gas is likely a result of AGN heating to the SM. And this oxygen 3 to oxygen 1 ratio show a smaller ionized gas fraction. And the oxygen 3 to nitrogen 2 line indicate solar metallicity of this quasar redshift 6. So I'll stop here and take questions. Thanks.
Thanks, Jianan, for a nice talk. We've time for very few questions. So one question is, do you think the CMB has any effect on the line ratios seen?
Oh, so the CMB?
Yeah, the CMB.
Actually, the CMB has some impact on the CO lines because actually I have read the impact of the CMB. It has only it only affects the very low frequency lines like the CO221. But from the modeling, we actually consider the CMB effect into it. So it has no influence to the CO slide. However, for the fine structure lines, I don't think the CMB have a very large impact on that, because the CMB only has temperature of 20 Kelvin. However, the excitation temperature of these fine structure lines are usually several hundred Kelvin.
Okay, some more questions. So why is the O1 derived star formation rates an outlier?
Actually, I have shown that from the oxygen 1, the C2 to oxygen 1 ratio, we find it is not comparable to the local samples. It is lower, which means the gas is warm. And also we find high oxygen 1 to 5 infrared ratio, which may be also the extra oxygen 1 emission is likely a result of other heating mechanism in addition to the UV photons from star formation. So it's likely that this high O1 luminosity has a contribution from AGN heating. So because this star formation rate are based on the assumption that all of these lines trace the far UV photons from star formation, so they can use to derive the star formation rate. If there is a significant contribution of the O1 to of the AGN to the O1 line, then this line will be an outlier. So this is also consistent with what we find in the line ratio and also in the oxygen 1 to 5 infrared ratio.
Okay. And then final question, would it be possible to carry out an analysis of the XDR versus the PDR and possible shock models contribution to the excitation of the different CO lines?
I think currently it's not possible for the high redshift 6 quasars because these quasars are not many of them have been detected in many CO transitions. So if we want to discriminate between the SDR and the PDR and also shock model, we need many CO detections, especially for the very high J part and also for the very low J part. So for these quasars, actually, we see that we only detect one of the low J CO, which constrain the PDR. And maybe in the middle, there's contribution from both components. However, for the high J, we only have 13 to 12. So I think this kind of analysis would be possible for the local AGNs, but currently it will not be possible for this high redshift quasars.
Okay, thank you very much. So just a few more questions on the Slack, so I suggest you answer them there, and then it's time for a coffee break there. So thank you very much again for a very nice talk.
Thanks.
So yeah, so we now have, what is it, half an hour break. And so in the break there is an opportunity for general networking events. And if you're interested in that, the Zoom link is in the, if you go to Slack to the general channel, there will be a Zoom link there. But otherwise we will continue at 10 UTC. So thank you very much and see you later.